The first two series, we try to cover a lot of fundamentals. We try to understand many things about neural network, especially the foundation in terms of how it works, what are different functions, and the structure that you would use to set it up. And we also introduced the concept of a trivia. Just in the tradition of trivia, I wanted to cover one more TED Talk. I would highly recommend actually over the weekend watching this TED Talk by Alex Wisner-Gross. It's he comes up with a plausible equation for intelligence. Primarily, he says that intelligence is a force. It's very similar to E is equal to mc squared, something which actually succinctly explains that. But in short, he says intelligence doesn't like to get trapped. Eventually, if you're thinking about superintelligence or if you're thinking about artificial general intelligence, the whole objective function or the fitness function for existence, and when I use a fitness function, the evolutionary fitness function in terms of how nature evolved, or what we're trying to do in terms of artificial intelligence, is it tries to maximize the future freedom to keep its option open. It just doesn't want to get trapped. So anything which exhibits this force or this function eventually can be known as AI. Everything that we're doing right now, though we like to glorify and classify it under AI, it's mostly statistical modeling and machine learning, right? That said, the agenda for today is, of course, refresh the first 2 weeks. Look far more deeply into the characteristics of data, because primarily there's no magic in the algorithm. The magic actually lies in how you actually set up the data, how you actually identify the features, scale those features, which is fitting to some primary assumptions to the model that you're going to use, and then hypertune those models. We're going to learn about different normalization techniques of bringing the data to accommodate the model, as against trying to model the data, and some regularization schemes. Before we get there, again, a quick rehash. As I said, every time we start, just to make sure that we remember everything that we have done, we go through what we did in the first 2 weeks. This won't be for every week. As we progress, I'm going to move forward. Quickly, again, same set of questions. What is a threshold function, and why is it necessary? Anybody? Like, what is a transfer potential? A thresholding function or a transfer potential is necessary to do something in your architecture. Why is it needed? The first one's a transfer potential, right? To combine all the information from all the nodes. That's right. The way you combine is you take the input from the previous node or input from the very first layer, apply a weight, which we call as the knowledge, and that's exactly what we're going to learn. It's not the input that we're going to scale, it's the weight where the knowledge actually exists. The ability to scale the weight is what is necessary for you to learn the underlying function. And combining the input from the previous section or a previous layer or from a picture or a text or some set of features that you've extracted with the knowledge weight that you're trying to learn is where the thresholding or the transfer potential exists. What's an activation function and why do you need it? The curve is not linear, right? It's non-linear. And why should the activation function be non-linear?
This was the part I didn't quite grasp myself, but you have to apply some kind of modification to data, and you have to sum up everything. Otherwise, you're just getting what you got in. Not changing at all, but something has to be applied to that data.
Right. Some curvature is necessary to fit all the data points. The first way to think about activation functions being nonlinear is that linearity just gives you a single line, and you cannot fit a single line through a scatter plot. You cannot fit a single line through dispersed set of data, right? You need curvature. Now the curvature can be just, a line is a curve, but it's a straight line. A curvature can just be linear, or it can be a quadratic, or it can be a polynomial, right? Nonlinearity actually exhibits the ability to demonstrate that curvature, or the ability to demonstrate the fitment through different dimensions that your transfer potential exhibits, and puts it out either as a sigmoid or as a tanh function or some nonlinear function. Sigmoid, the function, the activation function shown here is a sigmoid. What other activation functions can we use in place of this? ReLU, tanh, that is hyperbolic tan. Some of you are doing your homework. This is going to help only if you build up, and the reason I'm recording this is whenever you're not clear, you go back to the recording, right? Anything which actually exhibits nonlinearity plus differentiability can be an activation function. Why does an activation function have to be differentiable? That's correct, Tomas. Backprop, but what does it mean? The ability to pass information from end to the beginning so that the error can be minimized. In other words, the ability to find a gradient. I mean, when you actually backpropagating, you need to calculate the size of the error, the rate of change of the error every time you make a change to your weight. Small changes to your weight can have a magnitude of change to your error. You want to compute that rate of change of that error and minimize or optimize that error to 0 in such a way that you're only making enough changes to your weight across all parameters to move the error to 0. That's called gradient, right? So we actually looked at a gradient descent. The error function can be any error function. Right now, we are using error summa squared. It can be mean squared error. It can be cross entropy. This is what we learned. This is very important for us to remember, guys. I think we learned backpropagation where if you want to move from some data point over here to its minimum, you're actually doing a gradient descent. A gradient ascent is hill climbing. A gradient descent is going down the hill. We looked at some equations which actually allows us to calculate the error gradients with respect to the change in weight. We also learned that the change in weight that propagates back in a feed-forward neural network, which is this component over here, the error gradients will be really high for the layers which are near the output, and it'll start diminishing as you go back. It's called vanishing gradients. This is what we covered in the second session. So far, so good? All right. We also looked at supervised versus unsupervised. Unsupervised is the ability to not train the network, but let the network pretty much expose the internal data or the taxonomy or the data structure, like the clustering or the relationships or the distance metrics or the centroids or some kind of statistics about the data without training. That's unsupervised, right? You're not literally training with any pre-trained data corpus. In supervised, you're saying, hey, you know what? I want to actually train the network to do certain functions in a very general form. And when I mean that, the difference between training a network to do something very specific, where it can only predict for events that it has already seen, versus something in general where it has not seen certain events. For example, if you have, let's say, 5,000 different variations of cat's picture, and these are all different angles, different species of cat, different colors, 5,000 variants. You train the network on these 5,000 variants. When you want to actually send another cat picture, the network is considered overfitted when it can only identify a picture of a cat which is extremely similar to those 5,000 pictures that it's already seen. That's called overfitting. So you need to generalize the network saying, no, you've seen these 5,000 different variants. Now I'm going to send you a picture of cat which is not extremely similar, but it is still a cat. In general, I still want you to classify it as a cat. That is called generalization, where you regularize the network to do that activity, right? That is for classification. We also said for regression, you can still use the same feed-forward neural network for training. Any questions on the first two lecture series before we get to the concepts on the third one, in terms of how do you feature scale, what are the characteristics of data, and one or few ways to regularize? Tomas. No, there are many different ways you can actually set up. Feed forward is only one way of it. There is a recurrent neural network where the neuron can be connected to itself. You can actually you can have RBMs, you can have hop field networks. There are many different ways to actually set a convolutional neural network is a feed forward neural network, but the operations is convolutional. And LSTM is a recurrent neural network. You have retina nets, you have many different variations. But before we immediately jump to those variants, the reason I'm not actually saying these are all different types of neural network and really going fundamentally deep in one neural network, which is feed forward, I'm showing you some examples. We're going to do some Python coding today, right? I mean, at least I'm going to show you some Python code. I'm going to share the notebook for you so that you can go back over the weekend or during the course of the week and take some homework, which is some examples from problem statements in your own engineering, like simple things like, hey, if I want to predict the traffic, and I have data about traffic for the last 10 days, I want to do traffic prediction for the next 2 days. How would I do that? If I want to classify my students based on some cohorts that are pre-created, and I want to, given the same set of features in the traffic, can I now classify a new event that comes in to that cohort automatically? So you can actually take up some examples after today's session and do it yourself in your day-to-day engineering activities, right? We said the characteristics of data, and the data set that we spoke about was a wine data set. Today, we're going to teach our neural network to taste the wine. That is, it's going to taste all the features within the wine, and it's going to say, what's the cultivar, right? It's going to say, this wine is from cultivar 1, this wine's one. So we're going to actually develop a tongue or a taste in our network so that if these parameters comes in, values for these parameters comes in, it automatically tells you what cultivar it is. But for that, we need to understand what are the different features or characteristics of the network. And we said there are about 13 characteristics, starting from alcohol, malic acid, flavonoids, color intensity, hue. So you just pour the wine on the network, as in, not literally, but if there's something which analyzes this chemical, like there's a plate, you pour it, it analyzes the chemical, 13 different parameter comes out, goes in a neural network, and one of the lights of the cultivar bumps up, right? How do we do that? Notice that this is trained on 178 instances of parameters. That is, there's only 178 rows of cultivar 1, cultivar 2, cultivar 3. The first column is which cultivar the wine came from, right? The rest of the columns or parameters are nothing but those features. Are you able to understand the setup of the data? Everybody? All right. 178 parameters, that's it. Okay. Are there any missing values? No. The couple of things that you need to actually understand over here is the dataset characteristics is called multivariate. I mean, these are just vocabulary you're going to learn. There's multiple variables. So all the variables change. So it's multivariate. You could have had 13 different parameters and only one changes. That's of not much use, right? Then the dependent variable is only dependent on one single variable, one single independent variable. You can pretty much run a linear regression on it. Now, let's understand something about the features. Features, again, are nothing but those 13 set of parameters that we looked at. These features can be discrete or continuous, right? What's the difference? Just, it's a mathematical term. It's a really second grade, third grade question. Continuous is a real number. Discrete means it's 1, 2, it's a whole number. So features can be anywhere between 0 and 1, or it can be 0 and infinity, right? It cannot be a number as well. There's no reason it can be categorical, right? A feature can be red, good, blue. It can be a text. But neural networks cannot directly work with text data. You have to convert the text into some numerical form, which I'm going to cover in the next series. What are different ways to actually convert a categorical feature into numerical values that's meaningful for the network. But for now, I've taken only numerical features, which is pretty fine. It's mostly fractions. Now, the thing that you have to notice is that they're all of different magnitude. And this is the value of x that will be going inside, right? Now, the signal strength or the magnitude of one feature can overpower the magnitude of another feature, because your transfer potential is just saying x times some weight, and that becomes an input for your activation function, right? So this is not going to be a very stable network. I mean, so the magic is not in the network by itself, right? The data actually has strengths or magnitudes which varies between discrete and continuous, varies in size across features widely. That is, your proline characteristics is considerably always bigger than non-flavonoid. Varies within the same feature. That means primarily you can have the maximum and minimum. Let's say, look at this, 132, 89 within magnesium for cultivar 1, for cultivar 2, for cultivar 3, all varies the maximum and minimum even within the feature, or the differential or the range or the variance between across all cultivars within the same parameter also varies significantly. That is, the range can be big. This is not very good for the stability of the network, because if you notice, if I have to plot this as a signal on the right, the only signal that looks really prevalent is the proline. The rest of the signal is almost hidden over here. So far, so good. So no matter what you send to the network, it's almost as if proline is going to take over as the independent variable that will be signaling the dependent variable, which is not good for the stability, right? What do we do? Scale the data, correct. Now, there are different ways to scale the data. There's something called range scaling. There are three large buckets of scaling the data, right? There's range scaling, there's normalization, or there's standardization. Literally, if you want to kind of work at the very highest level, you can squash the range to belong to some A and B. You can normalize the data using the distance metric of the features within the data and not try to squash the range. Or you can use a statistical technique called standardization. And there's nothing wrong with any one of it. If the unscaled data look like this, where proline over here, I don't know whether it's, is actually increasing the signal strength, I would pretty much use, let's say, a min-max first to see what happens to the data. This actually scales each of the value between 0 and 1. It just takes every parameter, squashes it between 0 and 1. All it is doing, oh geez. I scaled my data. All it's doing is I mean, there are two techniques. You can take every feature and reduce the x min or x bar. X bar is the mean, right? You can either say x minus x min by the range, which is max minus minimum, or you can say, reduce it by the mean. When you reduce it by the mean, it actually, puts it within the range of 0 and 1. And then this is how the data would look like if you do that. Literally everything is having a value between 0 and 1. Every feature. We don't know whether it's good or bad. It depends on the model you're going to use. If you're going to use linear regression models, it has certain benefits to it. If you're using classification, in our case we are doing the classification, it has certain benefits to it. We run this scaled data. You can do pre-processing. You can run the scaled data through some pre-processing to find what you call as log likelihood, or LL. A log likelihood is nothing but the inverse or the reverse of probability. How do we understand log likelihood or likelihood function? First, we say, given a set of parameters which are independent, there's given a set of features which are independent, what's the probability if I have features x1, x2, x3, and some target approximation function y? We are saying, given the values for the set of input features, what's the probability that the dependent will take a specific value? That's what a probability function is, right? The probability function is actually computing the theta, where theta is some transfer potential from the feature space of xn. So far so good. That's what probability is. Likelihood is just reverse of it. Given a value y, that is, you already know the y and some distribution of y, what's the likelihood that it came from a feature space xn, which we call as L theta, which made this value y possible? It's just saying probability in a reverse way. Probability is given a set of features, given a theta, what's the probability that you're going to get a target approximation function? Or if you already have a target approximation function, what's the likelihood that it came from this theta? The natural log of that likelihood calculation is called log likelihood. In classification, we use log likelihood to see, given a cultivar, what's the likelihood that it came from the feature space xn, or L theta, where theta is some transfer potential. So far so good. Now this likelihood, the larger the likelihood, the better the fitment, right? The likelihood should be higher for you to say that these set of xn, or xn being features, fit this cultivar y, whatever the cultivar wine 1, 2, 3, 4. Now the way we're gonna, all right, I'll show you how to compute this log likelihood, maybe mathematically as well if interested, but otherwise there is packages in Python or in many different places where you can just run the scaled data and say what's the likelihood function for this. Notice that for classification problem, there are different likelihood functions. Every time you scale the data, you can actually run it through a likelihood function, a log likelihood. It's going to give you some number. Then you know which one of this is actually a better fit. The unscaled has a log likelihood of -82. That's really small, right? It needs to get closer to 0. It mostly likelihood function, if probability function is 1, the likelihood function would start from negative going towards 0. So -82 unscaled, because that's not a good signal. Then we min-max it. It gives me a log likelihood function of -5, closer to 0. Okay, scaling helped a little bit. Or I can actually use something called unit norm. That is, I can quash that row, the row that we see here. I can take this row, I can scale it down where each of it adds up to 1. I want to convert it into a unit vector, right? Which means everything scales down in such a way that when you add up all these values, it adds up to 1. That is called L1 norm. Very quickly, for us to understand L1 versus L2 norm, if I have 2 points, wow. If I have 2 points, let's say, x1, x2, L1 norm is nothing but, and if this is the 0 as an origin, it's the absolute distance. This is 3, this is 7. It's the absolute distance by tracing the path to the origin and back. That's called L1 norm. L2 norm is the sum of squared distance. It's a Pythagoras. You know, if you have a square and b square, it's a square plus b square equals c square. So root of that is the L2 norm. What it does is the unit norm is the scaled sum squared of the values that you have over here. If L1 norm actually reduces this to a number which all adds up to 1, for L2 norm you need to square it. The squared sum of it should become 1. I'm using L1 norm, right? There's no reason why you can't use L2 norm.
You square it before or after you scale?
After.
After.
Yeah. All right. So what I'm doing over here is L1 norm. It's useful in certain places. First, let's look at what happened to the log likelihood, and we can also visualize. So if you notice, the way we compute the L1 norm, the equation is you just take for L1 norm, you take the squared sum of all the values, but you actually go to each one of these. So why are we taking the squared sum? Because that's a distance metric, right? And you go to each one of this parameter and just divide it by that. That will give you the L1 norm. Now, when we actually look at the L1 norm, look at what happened to the data. Compare it to your unscaled version. You can actually visualize it. You don't even have to know why the signal. Each of the signal. So imagine that this is now getting pulled up, like you're trying to straighten this line. When you actually try to straighten this line, everything underneath it should also align, right? So typically that's what's happening over here. If you notice here, you know, most of the functions were quashed, or most of the parameters were quashed. But as soon as you try to normalize this by pulling it up, this got pulled up and everything else got pulled up. But it is still having that same effect, even though everything actually came down to less than 1. From a signal perspective, that not a single parameter will actually significantly influence your activation function. The probability of the weight actually increasing for the functions over here and the weight actually reducing for the functions over here and still keeping the activation low is very high. Are you able to follow what I'm saying? If you had the unscaled version, this is something like 1600, right? Then the weight has to be extremely small in your transfer potential. And the weights for all of this should be extremely high. That's going to make the networks really unstable. Here, because all the values are between 0 and 1, because it's less than 1, the transfer potential will always be working with an x of value between 0 and 1. But still, some of this is closer to 1. It's 0.8, and some of this is closer to 0.0. Better place. What did the log likelihood look like? It literally reduced it significantly. Min-max reduced it further. But we're going to see if there's a better alternative, right? You just don't stick it in, right? This can be for anything. This can even be for TF-IDFs. This can be for your BM functions, right? There are tricks where you can take the standard linguistics and still normalize the data in such a way that you can get better centroids or better topic models or better distance metrics. We're going to cover that when we look at linguistics. But for now, there's one more technique which might be helpful for classification, but it's really bad for regression. We'll cover, when we do regression, I'm going to cover why this is going to be bad, right? But what is standardization? All standardization is doing is, I want to actually bring everything, if the mean of this is somewhere between 0 and 1, and the mean of this is somewhere between 0 and 1750, and the mean of this is somewhere between 0 and 1, I'm going to bring all the mean, the mean value of all of this parameter to 0. So first I'm going to bring it to 0, then I'm going to reduce the variance to 1 standard deviation. That's called zero mean unit deviation, or zero mean unit variance. You're going to reduce the variance. So far so good. The reason we do this is because we want, we want a line which is the mean line over here, and we want this, when you actually look at this as a Gaussian, we want 1 standard deviation, where everything fits within one standard deviation. What it does is something very beautiful for your network. When you eliminate the mean and you actually bring the variance to 1 standard deviation, you're saying that I'm going to help the network stabilize by retaining the variance, but still bringing the values closer to 0. It is not going to be contained between 0 and 1. It's not going to do that. Whatever is 1 standard deviation, it's going to retain the range will be that 1 standard deviation. It's going to reduce the asymptote. This is the asymptote, right? This is not, it's going to eliminate outliers. It's going to quash the outliers. It's going to reduce the, if you look at a box plot, you'll not see a whisker which really goes long. That means you don't have an asymptote. That stabilizes the network for a reason, because there is predictability for both your transfer potential and your activation function.
How well does that work if your data doesn't follow a normal distribution?
That's a great question. The data should actually have some characteristics of linearity and some characteristics of normal distribution. There are techniques called power transformations, Box-Cox, Wilson, and other techniques in statistical modeling, which actually help you normalize the data. But that's a great question. Are there any limits on using? There is none, primarily because the first pass on the ReLU will actually get a smaller magnitude, because ReLU actually goes from max to 0, and anything below 0, it's still going to keep it as 0. And the potential of it not having a exploding gradient. ReLUs have exploding gradient, right? If you did not actually standardize, are you guys able to follow what I'm saying? ReLUs are rectified linear units, and rectified linear units have a nonlinearity like this. That is, if the transfer potential has a value 0 or less than 0, then it's going to be 0 all through. But if the transfer potential has some discrete or continuous value, it's going to retain that, right? That's what a ReLU is. That's a rectified linear unit. And his question is, are there any pros or cons in using this for ReLUs? Look at the probability here. When things are negative, it's still going to be 0, but things are not always negative. Very similar to a hyperbolic tan, right? When things are positive, that is when your transfer potential is actually giving a value which is positive, and activation function being ReLU, it's going to retain everything over here, right? So, and it's not going to explode primarily because anything over here is actually within the value of 1 standard deviation. So the magnitude is not like 1760 or 1 million or 2000 or whatever. The magnitude is still taking every single neural node in your neural network to be contained within that 1 standard deviation variation. And the network is finding sparsity for anything which is below. So the probability of the network being sparse, at least on the first pass, is around 50%, which is a very healthy network, which is good for feature scaling, right? Look what happened to the log likelihood. Came very close to 0. So we're saying, okay, fine. Seems like it's better than unit norm or min-max, better than scaling. There are different ways to scale. So far, so good. You're following? Go ahead, David.
That's kind of what I want to address exactly. This happens to the end of the dead node.
You end up with sparse nodes. We wouldn't call it as dead nodes if you have not added a bias. So the reason why, and let me clarify, when you say dead nodes, nodes which run to 0, that's what you mean, right? Yeah. The reason, if you don't use a bias in your neural network, you will actually run to it. Or maybe you want to purposefully run your nodes to sparsity because you're trying to find features which has the highest mutual, which has the highest entropy for the dependent functions. And that's a good thing. That is how you actually use the network to find useful features. I'm going to cover that in this section. Any questions? Are you guys able to visualize this in terms of how transforming the data is first thing that you do? This is called pre-processing, right? And primarily what you do in your modeling is you pre-process your data. Even for neural networks, you have to pre-process. Well, you can write pre-processing neural networks. I'm not going to cover it in this one. You can actually say, hey, my first neural network is actually going to look for multicollinearity, normalization, some power transformations. It's a neural network which identifies what function is necessary, I mean, by the virtue of the black box, changes the data to cascade into a neural network where you're actually using it for prediction. Not get there, but that is possible if you understand how to set up pre-processing neural networks. But in the absence of that, you can actually go ahead and quickly do this. I mean, this is not a brain dump. You can go ahead and pre-process the network. That's a great question. The question is there a biological equivalent for something which actually normalizes the data? And there is. If you look at nature, if you look at golden ratios, if you look at anything, there is always a biological equivalent. For example, your hearing. You can't hear all range. It's, I mean, the auditory frequencies that's available out there, imagine if you can actually hear every single frequency. The ability for you to actually identify the signal, the noise would have been impossible, right? You cannot actually see everything. Again, there is a visual range in which you perceive. So any input function that you have as a human being, you touch, I mean, you cannot always perceive air. I mean, there's friction in air. Every time I move, if I keep feeling the friction, it'll be like you're moonwalking every time, right? So there, by the virtue of evolution, by the virtue of the math of the evolution, pre-processing has already happened in such a way that you're given the filters to cut out noise. You're given the filter to convert that. What's the game that was played where they actually altered Laura versus Yanni? Where you're actually, have you heard that when you juxtapose two frequencies where one person's saying Laura, another person's saying Yanni, and you kind of quash that, you play it. Some people hear Yanni or some people hear Laura. I mean, even your brains are wired in such a way that it pre-processes data and picks up signal it wants to signal. I'm pretty sure there's so many examples which I'm not qualified to even comment on, but yes, there's a probable explanation for math in everything we see, right? So that's what we did for input. Again, the 100 different things you can actually do for input. We can learn that, as Josh actually asked, what if the data is actually not in a form where you can easily find a Gaussian, right? Then we have to do different things. But for now, let's assume that you can actually apply some scaling on the functions. Even for output, now the output was a categorical value. It was a value, the cultivar was 1, 2, 3, right? But when you actually try to send the values 1, 2, and 3 to a neural network, you're also sending some signals, because 3 is of higher magnitude than 2. 2 is of higher magnitude than 1. When you're actually asking, when you're setting up your network, and you're saying, you know, given a set of input functions, either choose, oh, what's happening? Either choose this or this function. There's some weird thing happening there. Then you're saying the magnitude of this should be 3, for this should be 2, for this should be 1. When you actually look at error, the error deviance for 3 probably will be larger than 1, or vice versa. That's just wrong signaling to the network. I mean, so the numbers like 1, 2, 3 in your output, if it's classification, are not really of any order or any magnitude. They should all be treated equally, right? So then we have to convert the output also into some normalization, not just input. Before you train, you should also convert the output to some normalization. What we do over there is called encoding. So there is one standard way to encode. It's called one-hot encoding. All it does is it starts giving, for 1, 2, and 3, instead of 1, 2, and 3, it just bitmaps it, or it provides a vector where one bit or one value of the vector is set to 1. So if this vector is actually used for any kind of computation, summation will sum it to 1, you know, or if you're trying to use this vector for any transformations, you're still the strength of the vector is still 1, but the information that you've coded in such a way that only 1 is active. That is what I said in the beginning. There is no reason why the input data does not have to be categorical. If it is categorical, there are techniques. One-hot encoding is one of the techniques, but there are other techniques that you can actually apply for input data. Labelizer, hashing, binarizer, there are so many techniques. Or you can actually take all the categorical data, look how they're actually dispersed relative to some other function, and just take the distance metric. There are many different ways, right? Text is where you actually fall into this category. Even if you actually work with characters, there are 26 characters to deal with, right? The combination of the 26 character can be a probability function. You just take the probability as an input, right? So I will not cover what if the input data is categorical. I'll just cover what if the output data is categorical, because in classification problem, output data is categorical. In a regression problem, output data better be a real value, right? Classification can be a real value if you're actually using binary probabilities, like a logistic sigmoid. Even there, you're actually sending a value 0 or 1. Here, what we're saying is we're setting up an, instead of setting up a network with one neuron predicting 1, 2, or 3, we're going to add 3 neurons where only one neuron will be 1, the other 2 will be 0. That's what we are saying. That's how you're going to set up this network. You understand the difference? Your output neuron has the ability to predict any number, right? So if you have a target approximation function with millions of classification, you can still have one output neuron. But the problem with that is the magnitude. Go ahead, Rachel. Pretty much that's what I'm going to explain. Your softmax function always is a probability, but when you train, you don't give probability. You give a probability of 1. You don't give a real value, right? What is a real value? A real value is a value between 0 and 1, because a probability is a function between 0 and 1. So when you're training, you're saying the probability of the first node is 0, the probability of the second node is 1, the probability of the third node is 0. That's exactly what you're saying when you're training for the neural networks. But when you predict, it's not going to come out that way. When you predict, see, the sum of these three should be equal to 1, right? We need to ensure the sum of these three is equal to 1, because if you actually make each one of this output function a sigmoid, let's say, there are many different ways to actually design this, right? The activation function of the output neuron can be anything, but we want it to be something meaningful, which predicts 0 or 1. So there are multiple ways to do that, right? I'm going to use probably this empty slide. So now we know we need 3 neurons as against 1. And we know that when we are training, when we set a bunch of 13 values into the feature, the output of this will say the probability of this is 1, for this is 0, for this is 0. That's how we're going to train, right? So that the network actually learn the probabilities. Now, each one of this should have an activation function, correct? So far, so good. What should the activation function be for the output is a question that we ask. Can it be a ReLU? ReLU goes 0 to infinity. Maybe not. Tan H, which is hyperbolic tan, -1 to 1. Sigmoid seems to be one approach. But imagine if each one of this is a sigmoid that is going from 0 to 1. Then there is a probability that this can be 0.8, 0.6, 0.7, right? If you make each one of this a sigmoid, it can learn, even though you're actually saying learn 0 and 0, because you're generalizing the network, or because there are statistical anomalies or signal and noise across all the 178 variants, your probability can come up to something like this, and you can say, oh, I'll just pick the highest probability to be the real probability. But is it true? That when you have options like this, you're still going to pick the highest probability? Or when you have options like this, that you're going to just pick the highest probability? This is quite possible when you actually pick up a sigmoid. Instead, what we want is the sum of this in this vector is equal to 1. We want a quashing function. We want an output normalizer similar to the pre-processing work that we did, that the pre-processing happens within the neural network where the output vector is quashed to a value 1. And that function is called the softmax. This is the softmax function. What it does, interesting. So what it does is, it's a form of exponentiation, right? If you have values of x1 to xn, this is the sum of all 1 to k or 1 to n, exponent, the sum of all the exponents of 1 to k or 1 to n of values x. But the individual value of x is e to the power of value of x1 by sum of all 1 to n e to the power of the z, whatever, this n. Z being the theta, which is this function. Are you able to follow what I'm saying? It's just sum of all exponents, but you're actually taking, let's do this again. Thomas, you were shaking your head. Was that a yes or a no? You're not following. Okay. Let's say I have 1 plus 2 plus 3, which is equal to 6. If I don't do any exponentiation, I say x1 equals 1, but the new transformed x1 equals 1 divided by 6. Just let's first go with the structure, right? before exponentiate. X2 equals 2, but the new value of X2 post transformation. If you can visualize this, the only thing that we are doing now, if you have 1, 2, and 3, is exponent 1, exponent 2, exponent 3, which gives me some of this, some theta function. This is theta equals all of these values. Now I'm going to keep this sum. Then I go to individual x1, which was 1. I'm going to say exponent of 1 divided by that sum theta, whatever that is. That's all this is doing. Softmax is just that. It normalizes in the log space. Exponent is a log space, isn't it? It's just another way to say log e of n equals k, which is nothing but e to the power of k equals n. That's all it is doing. Jesus. I don't know what's happening there, but I'm just saying, what is an exponent? It is nothing but this. Correct? Do you understand? Log, is this looking right? That's all it is doing. It's beautifully scaling the numbers in the log space. That's all the exponent does. It brings everything into the log space. That is, things which are nearer is really near, things which are far is extremely far. Why do we do that? Now I've given you that insight. Why do we do that for Softmax? Let me repeat that. In a non-log space, let's assume your values look like this, right? When you actually map, so this is your scale of natural numbers. Let's say I have a logarithmic scale and I want to map this. I'm just making this up, right? What happened? Things which are closer got really close. Things which are farther started getting much further. Are you able to visualize this? It's important to visualize this. If I had applied a non-softmax weighted average, what I showed you before was a weighted average function, right? Where I did not use the exponentiation. If I do not use the exponentiation and try to normalize in the Euclidean space, not in the logarithmic space, what happens? And why am I using the exponentiation, which is a softmax, which is in the logarithmic space? Why should I do that? Anybody? Just that's because of this visual insight, you guys should be able to deduce why that's important. You're close.
You don't want the error to overwhelm low probability.
You don't want the error to overwhelm low probabilities. What does it mean? If you had 3 nodes, and if the values were something like this, if you transform this in the Euclidean, it kind of will be in a linear weight, as in the transformation that this being the highest and this is the probable that I need to take will still be in a linear space. Soon as you move it to log, this which is closer to 0 will get even further closer to 0, and which is closer to 1 will get farther back towards 1. Are you able to follow what I'm saying? So we want to quash smaller numbers to closer to 0. We want to take numbers which are closer to 1 and move it very higher up when you actually convert in a logarithmic space. That's the only reason you use softmax. Otherwise, you could have just used a sigmoid and taken, if it's 0.98, 0.99, 0.999, in sigmoid, you can say, okay, I'm going to use this, right? Not very helpfully. How they're all equal. How did you? Because they went on the threshold of that sigmoid. That means the sigmoid activated. Because when you ask for a discrete class of that sigmoid, it is equivalent to 1, 1, 1. That means it's all cultivars. You don't want that. You want to quash it in the log space. Hence, you use There's something cutting me out there. I'll figure it out. Nathan, anything I write to the right-hand side doesn't work. But anyway, able to follow why softmax is important when you're actually trying to use classification. You just want to quash things in the log space. An exponent does that for you. It's just a natural log. So far, so good. Okay. Here is how I'm building the network. I'm gonna probably help you guys play around with the notepad I'm gonna share. But typically I'm using a framework called Keras. You can use TensorFlow. Keras is actually built inside TensorFlow since the last 8 months or a year. But I use the Keras package separately, where I've built 3 layers. This is the dimension. That is, I'm saying I want 13 input nodes. When I'm actually building a dense network, I'm saying I want to input 13 parameters. So dimension is 13. So what it first is going to do is it's going to give me 13 input nodes like this. Then I say that needs to be connected to some X number of hidden nodes. There is a scaling function, but for this exercise, I said, okay, double it, because the more complex the network, the better the behavior, right? I said, okay, whatever is the input function multiplied by 2, you don't really need such a complex network. It can actually be divided by 2, quash. I'm just saying, increase the width. I could have said, give me 8, right? You remember the thumb rule that we actually set up last time in terms of total number of samples, total number of classification that you actually need will give you some thumb rule in terms of how many input nodes you need. For this network, you don't need more than 4 or 5 hidden nodes. But I said, okay, give me 26. I said that the activation function for the hidden nodes is sigmoid. Notice that I'm saying the activation function for the hidden nodes is different from the output activation. What does it mean? That means I have some inputs that's coming in. I have some hidden layer. I want this dude to actually use sigmoid as an activation to the next node, right? But I want this person to actually use softmax. Are you able to follow what I'm saying? Which means your feed-forward neural network does not necessarily have to have homogeneous transfer potentials and homogeneous activation functions. As far as transfer potentials is concerned, by default, Keras is set up that the transfer potential is always going to be a summation. You have to go back to TensorFlow to change that, or you have to actually use certain templates in Keras to change that. But by default, if you're working on neural network, your transfer potential is always, mostly, going to be summation. But it gives you an option to change the activation function for each layer. That's exactly what I've done here. Are you able to follow? Now, I've also said that I want 3 neurons instead of 1 neuron, because I want 0, 1, 0, 1, 0, 0, 0, 1, 1 as my output, not 1, 2, 3 in the same neuron. And the activation function for each of this neuron is a softmax. Any questions? Okay. By the virtue of the setup, I'm already saying that. If you notice, here I said input dimension. By default, that's considered as layer 1. And this dense function actually says, okay, how many next the dense function actually says the number of neurons required in the next layer. That is telling you that's a hidden layer. Then you're stacking the same model. So the first model, you said model.add. So it's going to set up 13 plus 26. So your model will now have 2 layers. You took the same model object, you said add 1 more layer. So now it added some more layers. You can take the same model and you can say add. You can do this model.add any number of times. Are you able to follow? Right now I just did model.add twice. That means it's a 3-layered network. I'm using a loss called categorical cross entropy. Now the softmax does not work very well with mean squared error or error sum squared or any other functions from a stability perspective. I'm going to cover different types of loss functions in series 4 or series 5 because error analysis with respect to the activation function on the output network needs to be studied by first understanding what you call as bias versus variance trade-off. We already understood what's a bias and what's a variance, right, in the last series. You guys remember? What is a bias and what's a variance? If you want to think about it like a target, like we saw a picture. Anybody? Rachel? That's right. Perfect. So if your target is something like this, bias is when your data points are closer to this target. If it is over, if it's somewhere over there, it's funny. I don't know what's happening. Yeah. If your data points are closer here, then you say your bias is low. You don't want a high bias. You want a low bias. High bias is your data points are all over there. You want to reduce the bias. Sorry, you want to you want a bias which is closer to the center. So you want to reduce your variance. This is your variance. You increase your bias. So you want a high bias, but a low variance. So when you actually have things which are spread out, you're having a higher variance. You want the grouping to be better. Now, when you study your error functions, it has to be studied with respect to the activation function in the dimension of variance and bias. For that, we need to understand the mathematical model behind variance and bias, which I'm going to cover series 4 or series 5. But for now, let us say that I'm using a loss function which is give up. I'm using a loss function which is categorical cross entropy. You know, it's a fancy name for log likelihood. Categorical cross entropy is just a fancy name for log likelihood, a function which is based off log likelihood. And the reason why it has categorical is because you're using classification, which is a categorical data. Cross entropy is log likelihood. I'm using an optimizer called Adam. It can be SGD. SGD is stochastic gradient descent. I'm going to cover different types of optimizers. For this, I'm using an optimizer called Adam. The training is being set up in such a way that you have k-fold with n splits or 5 splits. This is data scheme. What is a k-fold? Last time we covered k-fold. Partitioning the data. Why do you need to partition the data, and what is k-fold? Rachel. That's right. If you have a data set, you can actually split the data set into n folds. And you can say, first, I'm going to use this as validation, but train on these. Next, I'm going to use this as validation and train on these. And I'm going to do that 5 times. The reason being, you don't want to train on the entire data. You want to first train on a portion of the data and set aside a specific portion for you to go back and see whether the network is underfitting or overfitting for the unseen data. It's the unseen data which actually tells you whether the network is underfitting or overfitting. And you can do that by setting n-fold or k-fold data partitioning scheme. It's called cross-validation, right? So I set the splits, I say split it 5 times. That means train the network in each epoch 5 times. I'm using a tensor board as a function to actually see what is happening within the training. I do not know whether I can switch and demonstrate that. I'm going to train the network with 200 epochs. What is an epoch? When you see all the events at least once, that's called an epoch. Like if you have 5,000 cats picture or 178 statistical attributes or statistical dimensions, 178 in the projection, that's called an epoch, right? When you train this, it says, okay, the validation, when I actually compare what has been predicted to what was the true value, is 93% accurate with 2 standard deviation. This is the mean accuracy across all the folds. Are you able to follow what I'm saying, Nitish? In one attempt, you're going to have 5 folds. That's what it means. And then I want 200 such attempts. And on the same data. But it's on the same data. I'm not changing my data. That's a great question. It actually does. But think about it this way, right? And that's a fantastic question that actually leads to series 5 already. Think about your data is not some uniform data, right? When we actually looked at, when you look at the data, there are 2 attributes to it. One is your theta or number of x that you have. Another one is the cultivars. You might have different distributions of cultivars for 178 values in the parameter space. When you take 5 folds, how do you cut this? Right? Do you take 1/5 of this, 1/5 of this, 1/5 of this? Or do you just randomly, take 1/5 of this? Or do you apply some other scheme so that there is an equal representation? Is where the function of k-fold actually gets far more interesting. Where functions like class overlap and class imbalance comes into play. I do not want to jump into that, but k-fold kind of solves that stratification problem for you in scikit-learn. You can actually go ahead and change the parameters of k-fold function in scikit-learn. What I'm using is the framework or the libraries that I'm using is called scikit-learn, which gives me default stratification of how to actually set up this k-fold, which stratifies based on the target function. But notice that this is just a template that I'm using. It still doesn't know what is the parameters that's going in and what's the target function. I have to fit this k-fold somewhere, and that somewhere is what you call a cross-validation score, another function, which takes this template and then stratifies it before training it. That stratification scheme is a function of the cross-val score or cross-val predict and the type of cross-validator you're using. And there are many different types of cross-validator. I don't want to jump to that because data partitioning is an art in itself. You can literally mess up models by not normalizing your data. This can be any model. Give me a model, I can tell you how you can mess it up. Just not even looking at the model, right? And even before you choose a model, you need to make sure that the partitioning scheme and the normalization scheme in the pre-processing is done right. And the model is having the right assumptions which can take that scheme in. You cannot just generally say, oh, today I'll use this, tomorrow I'll use that because somebody used it, right? Now, I could hit an accuracy of 93%. To analyze this, I need to understand a few things. What is accuracy? What is type 1 and type 2 errors, and so on and so forth. How are you guys doing, generally? Or is the information, for some of you it's basic, for some of you it's new information, for some of you it's balanced, and because there's only X amount of people, it's easy for me to partition it. How should I go faster? Should I go slower? Should I go more deeper? What should I do? Or is the pace right? The pace is about right? Okay. Okay. You guys just have to bear with it. Let's understand the concept. Because this is classification, there are different types of concepts that we need to understand in terms of error analysis. In regression, there's only a distance. How far are you from the real value, right? Because it's a number. In regression, everything's a number. In classification, let's understand a few things. True positives, true negatives, false positives, false negatives. This is very important for you to understand. It can, even for me, sometimes it gets confusing. I've been doing this for, I don't know, 17 years. And sometimes it like, what did you just say? And then I had to go back and fit it in my mind. Let's assume that there are two spaces, right? Selected items is a space which is the circle, and the real space where the positives and negatives are classified, right? Let me not mess this up. There is a circle which is the selected items or predicted items. And there is a box, outer box, which is true representations. The outer box has relevant and non-relevant items. Given 13 parameters and some values for these parameters, let us say the cultivar, one cultivar belongs to the relevant box, two cultivars belongs to the non-relevant box. So far so good? For this, for a single record, there can be only one cultivar which is relevant, correct? Two other cultivars is non-relevant. Following what I'm saying? So there will be some data point over here and some data point over here. Now, your prediction should be something like this. No data points from the non-relevant and one data point from the relevant, the right cultivar, for the set of inputs that you're actually getting. If it is like this, then one of the values that it selected was relevant. One of the values that your model selected was not relevant. That is, if there are two neurons enabled, both can be wrong. One can be right and one can be wrong. Which one is right, which one is wrong, depends on what's the true positive. So far, so good? Now, typically for a softmax, the predictions are always going to be 1, 0, 0, 0, 1, 0, or 0, 0, 1. So you will not get into the problem that I'm trying to explain here. But if you're actually looking at a query retrieval problem, you have a query and you have X amount of matching documents. There are 100 matching documents. There are 100 non-matching documents. If you dip into the pool of documents for a particular query, pick 80 from here and 10 from here, some 90, let's say that's the recall. Then we say that 80 are true positives, and the 10 which got predicted as if it's a positive is not a true positive. It's a fake or a false positive. That's what it predicted, saying, this is a positive thing. Out of which, when you went to look into the relevant and non-relevant, you said only 80 is actually really true. 10 is not really true. That means it's falsified. True negatives are things which were left out that was not predicted, that were also non-relevant. So they are true negatives. Things which are not predicted or not selected and were also not relevant are called true negatives. False negatives, things which were left out from prediction, from your recall, but were supposed to be part of your prediction. Things which are left out are negatives, right? Things which were selected are positives. Things which are left out are negatives. So those are false negatives. Why did you leave them out? Like, you shouldn't be leaving them out. So those are false negatives. So that is like a confusion matrix, right? Positive, negative, left out, not left out. There's a reason it's called confusion matrix. After some time, I figured out why it's called a confusion matrix, right? But are you with me on true, true, false, true, true, false, false, false? No? Kinda. Let's assume I have a blood sample. I am a doctor and I do not know where the blood sample came from. I'm doing a test on it. I do the sampling and I say, this person's pregnant. Okay? Now, the person can truly be pregnant or is not pregnant. If the person's really pregnant, I predict pregnancy. Is it a true positive? The person's pregnant, I predicted pregnant. It's relevant, and I predict it correctly. The person's not pregnant, I predicted pregnant. What is it? False positive. Positive because I predicted pregnancy, but that's not true. If the person's a man, I predicted is pregnant. Think about it. The person's a man, I predicted pregnant. Still a false positive. It doesn't change anything. The equation is because you're just having two variables, right? Pregnancy or not pregnancy. And the Boolean state whether the person is or is not pregnant. Now, if you increase that to more than one possibility beyond pregnancy and non-pregnancy, then you'll start getting into the values of true negatives that you actually left out another possibility, or you include a possibility from the relevant set that is not true, right? If you look at this box and probably keep looking at it for about 10 minutes every day, you will get the idea of positive means predicted from relevant or non-relevant set. Exclusion will actually tell you true or false. Okay? Now, there are some equations that you have to follow. Predicted positive means 2 positive plus false positives. That's nothing but prediction, right? That is, if you had 80 over here, 10 over here, your predicted positive will be 90. But 80 were true positives, 10 were false positives. Precision and recall, very interesting. Recall actually says what was predicted, right? That, let's assume I had 10 dog pictures which were all relevant. I predicted 8 as dog. That means the true positives versus relevant items is my recall. Recall rates of 1 is I'm recalling everything. There were 10 dogs, I'm recalling all the dogs. But it's not necessary all the time. If you're only going to show 2 dogs at a time, like if you're only going to show in your query if there are hundreds of documents, and if you're just going to show 10 documents at a time, you don't want to optimize for, go get all the 100 documents, go get all the million documents, even though I'm showing 10 at a time. I'm going to use some progressive disclosure to say one after another, right? You don't have to do that. But you want to improve the precision. What is precision? What is predicted positive? Predicted positive is a number that is coming over here. That is, you predicted some true positives and false positives, which is actually helping you normalize the true positives on the top. So you have a total prediction. You had, let's say, 80 plus 10, 90, right? That is your total prediction. Out of total prediction, what percentage of prediction were truly positive? So it will be 80 divided by 90, isn't it? That's a good precision. If you have 8 divided by 90, you predicted 90 things, out of which only 8 is true, the precision's really bad. Are you following what I'm saying? You want to focus on precision in most of the machine learning problems, most, not all. Totally depends on the business value of trying to recall everything. Say, for example, I'm predicting cancer, okay? The probability of, so let's say the cancer has a payoff function, right? The payoff function is you're supposed to take some medicines. And the medicine has some fitness function, which is there's a cost for the medicine. The cost can be the amount of value, the price you pay for the medicine, and the impact that has on your body. So these are 2 variables. There's a medicine. If somebody predicts that you have cancer, you have to take medicines. There's money involved, and when you take those medicines, there are some side effects involved. Okay, given the scenario, somebody comes in with a blood sample. I predict that the person has cancer. Now look at, if the person really has cancer, true positive, it's a good thing. If the person does not have cancer, then there is a payoff function, which is he goes through a psychological trauma, okay, fine, that drama can be evaluated. But he has some money that he has to put aside, and there is a side effect of consuming that medicine. The question is, what is that cost if you predict that wrong? That is one thing, right? The second thing is, I do not predict cancer. So I predict cancer, the person may or may not have cancer, correct? If I predict cancer, if he has cancer, everything's good. I don't predict cancer, the person doesn't have cancer, everything's good. I predict cancer, the person doesn't have cancer, there's a cost function. I do not predict cancer, and the person has cancer. What kind of error is it? I said false negative, right? What's the cost of it? It's not the price, because he didn't take any medicines. It's not the side effects that you're really worried about. The person's going to die. Now, so given this setup, am I actually what should I increase? Now, I've given you the setup, right? Think about it as a mental exercise. Should I increase for 10 patients? Should I increase precision, or should I increase recall? Should I increase accuracy? I'll come to accuracy very soon. Rachel? Did you hear that? If dying is the most expensive function, I should increase recall. Why? I do not want this scenario where the person has cancer. I'm saying you don't, I'm excluding you, you may not have cancer. This is the scenario, right? I don't want false negatives. Which means this box better keep increasing. If this box better keeps increasing, I have to increase my recall. I have to increase my recall rates.
Another way of thinking about it, you're willing to sacrifice your false positive, or basically increase the false positive in order to decrease your false negative. So your precision is getting worse because you're adding false positive, but at least you're not losing those false. Right?
But you will land up with a function like that if you do that. You say, I don't care, everybody takes cancer medicine, but the way you put it should be extremely balanced. So everybody should take cancer drugs, right? I mean, what's the cost? I mean, you're not going to die, but there's going to be side effects. That's where the business value comes in, saying, what are we optimizing for? I can make my predictions like this, or I need to make sure that there is enough coverage over here at the cost of increasing something over here. Is that how we're going to optimize? Again, that depends on the model. But totally that question that you ask in terms of what are we going to optimize for is a function of what is the payoff and what is the cost. So you want to increase the recall if death is involved. And there is some amount of insurance which is covering your cost of predicted cancer, but not having it. If you're predicted cancer, not having it, what's the error classification of it? Predicted, but correct. If that has some kind of a buffer, insurance, discount rates, then you want to go ahead and scale your recall at the cost of false positives. I can come up with a completely opposite example, right? Where recall is not that important. It's okay to have false negatives. For example, your document classification, right? Not document classification, your query retrieval. I don't want, it's not necessary for me to retrieve all the million documents. But the documents that you retrieve, that you're recommending the student, that this is the right document, even if it's only 5, better be highly precise. Are you following what I'm saying? So the precision matters there, not recall rates. When you recommend something, it better be of high precision. I promised you 1 hour, but it seems like it's gonna. Any questions? You can always come throughout the week. You can come to me and ask me. There's also an error contingency table specifically built for confusing you even more. It's actually called the confusion matrix. But the more you study this, the better you get at classification problems. And this actually gives you almost all probable conditions or contingencies for you to analyze for your business case based on the cost and the payoff for type 1 and type 2 errors. Based on that, when I ran my network, it gave me a 93% accuracy, and also these bumps are nothing but the k-folds. It starts with, my network starts with very low accuracy and saturates somewhere. Then the next fold comes in, it drops again for that fold, saturates somewhere. Look at the loss. The loss starts with the highest for the first fold, saturates down, closer to 0. The loss has to run down to 0, isn't it? This is for the next fold, next fold, next fold, like that. And in this overall confusion matrix, the strength of the color of this diagonal is what matters. Typically, each side of the diagonal should be extremely white, and the diagonal should be dark blue or whatever color that you're looking for. That means it accurately predicted the true labels. But in my case, the prediction was off for cultivar 2. Instead, it predicted one label as cultivar 3. That's why the accuracy is low. If you look at the confusion matrix, 20 out of 20 cultivar 1 labels were predicted correctly. 15 out of 15 cultivar 3s were predicted correctly. But only 23 out of 24 cultivars for true label 2 was predicted correctly. One of it was predicted as cultivar 3. What's the cost of that? Okay, it's fine, right? You can also normalize your confusion matrix to actually identify the accuracy of your network. So it's about 96% accurate, 93% accurate, not necessarily 96. Any questions? This is another way to visualize how your network is performing. I would quickly probably show you the so let's assume I haven't started my training. All right, this is my visualization. My last training actually looked like this. Now what I'm going to do is I'm going to not run through every single line of code, but I've given you, I'll share this notepad with you where I've loaded the data from the wine data set. There are about totally 59 type 1 cultivars, or cultivar number 1, 71 cultivar number 2, and 48 cultivar 3. This is the unscaled view of the signal strength of each of the cultivar. We realized that standardization was a good thing for classification because we ran it through what you call as a likelihood function. There are some statistical models that you can use as pre-processing. I've used something called stats model, and I've used multinomial logistic function. Binomial logistic function would have predicted only 2 cultivars, cultivar A or cultivar B. That's nomial. Multivariate is different from multinomial, right? I need a multinomial logistic function which predicts more than one output. So in the stats model, as a pre-processing step, I want to see if my standardization actually gives me a log likelihood. Oh, Jesus, slow. That is closer to 0. Don't worry about these p-values. P-values are good for linear regression, right? P-values should, I'll explain you what p-values are when we come to linear regression, probably not today. It should be less than 0.05. And I need to explain to you what is analysis of variance and so on. Coefficients, everything. Coefficients are tight, which is good, but don't worry about it. The only number that I'm worried about right now is log likelihood. And there's a reason why it's called pseudo R-square. R-square is actually a coefficient of determination for linear regressions. This is a classification problem. So there is something similar to R-square called a pseudo R-square, which says, is this a good fit? An R-square or a coefficient of determination closer to 1 is an extremely good fit. If R-square is low, that means it's a bad fit. These are only 2 numbers I'm interested in. So every time I actually want to run something in a neural network, the first thing I do is it linear regression or is it classification? If it's classification, I'm going to look at these 2 numbers, log likelihood, and you can kind of, jazz hand the pseudo R-square. But As long as this number is getting low, then I think I've used the right standardization. Then I take the data. I'm encoding, one hot encoding the output so that I get 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, whatever. I built my classification model for 26 hidden units using a better optimizer than stochastic gradient descent. I'm going to cover different types of optimizers and the mathematical reasons why one works better than another. I've set up 200 epochs, but let's start with playing around the data for the next 10 minutes, and I'm going to end it there. So let's start with an epoch 10, and for the heck of it, I'm going to make this a ReLU. I'm going to make this an SGD, okay, and see what happens to the accuracy. Ignore this number. First, I'm going to run this. I'm running my network to compute an accuracy. These things will stay the same. The standardization and so on. So the star means it's still computing the network. When I use only, look at, you see the baseline over there? Is this visible? Standard deviation about 10. With 20 epochs, SGD, I get accuracy of 34. It's not good at all, right? Now, there is something called grid search. If you don't understand the math, typically the first thing people do when they don't understand the math of the neural network is exactly this. They know how to set up, they've learned everything, they know how to use the APIs, they'll start playing around with this. Oh, I'm going to do this as Adam. And I'm going to run this again. I didn't change anything, I just changed the optimizer. 53%. If I had used some other optimizer without understanding the mathematical reason why you do that, which is why I think the mathematical reason is important, you would have got a different number. Then you'll try to throw some other stone, say, okay, fine, I'll try something else. It's not a good way, but most of us actually work that way. It's not bad if the optionality is small. But the problem here is epochs, optimizers, loss function, transfer potential, regularization, decay rates. I mean, I can keep going on. As soon as you start increasing this space, then why things are going up and down without understanding the math is not helpful. But for now, let's assume, okay, Adam's better than SGD. That's all I understood, right? Then I would say, is there something I can do with this dude over here? Maybe I put this back to SGD, change the activation function for my hidden units. So I put the optimizer back to SGD. I changed the activation function for the hidden units from ReLU to sigmoid. Previously it was about 32, I got 39. So magically, even without understanding math, I'm like, okay, sigmoid somehow better. I don't know why. We'll understand why later. So that in your mind, you know some way to actually choose model a priori. You just don't start throwing models at things because you saw some number somewhere else. Okay, so if sigmoid was better and Adam was better, I'm going to retain sigmoid and Adam, right? So this concept is called grid search. And you can actually, there is a framework which actually does that for you. You can just say, here are all the optimizers, here are all the weight values that you can initialize. Here's all the transport potentials. Here's all the, that bumped you to 71. Structurally, I chose some right equations. So far, so good. The only thing I can play around with is things like batch size, epochs, and k-fold, right? Let's see if epochs actually changes anything. Oh, did I rebuild the estimator? No, I did not. Sorry. So, yeah. Change the epoch to 100. Oh, because it's 100, it's going to take more time. Go ahead. The one with the highest accuracy on the baseline is the one we're going to use. So accuracy, no, there are F1 scores, there are accuracy. So the one that meets the criteria that you choose, which might be accuracy is one measure, but precision, recall, F1 scores, usefulness, you pick one, right? And then you keep training the model to improve that measure. In this scenario, I'm just, because this is a simple network, there are a few things I can change. I can change my batch size in terms of how often should I compute my error. If I want to compute my error for every single iteration, then I set my batch size to 1. Let's see what happens if I set my batch size to 1. I can set my batch size to 100 for every 100 iteration. I can set my batch size to something where after accumulating errors for 10 iterations, then compute the error gradient, right? There is no guarantee that 10 or 1 or 5 or 10, whatever is the right number. This concept is called hyperparameter tuning. But there is a set of gut feeling or an intuition, a mathematical basis that you need to develop before you randomly hyperparameter tune or randomly throw models at it. In the next set of series, I'll tell you how you could actually have predetermined not to choose ReLU over sigmoid. How you could have probably predetermined to choose batch size of 5 or 10 as against every single iteration. So the amount of time it takes for every single iteration is high because it has to compute gradients for every single iteration as against every 5 iterations or as against every 100 iteration, right? And there's also a way to actually initialize the network. Do you remember network initialization? Last time we spoke about Glorot or Xavier. That is, you can actually set the network to all 0 values, then the network is useless. There's nothing to learn. It still is 91. So there was no reason for me to actually compute the error. I could actually now start making the network more efficient. How efficient can it be? Can it be 50? So all I'm doing right now is hyperparameter tuning. I don't want to cover the next set of slides, which I had actually prepared. I'll do it 2 weeks from now because next week I'm off for a leadership offsite. I'm going to cover the basics portion of this, plus I'm also going to cover linear regression from first principles. I'm going to cover the mathematical intuition of how to actually choose the right model right off the bat. Notice that by batch sizing 50 still, I did not lose anything. I got more efficiencies, right? Any questions, guys? I'm going to share this notepad. I need feedbacks in terms of how fast or how slow, how deep of a math. I still propose that you kind of sit through the math functions even if it's a headache. And the more you sit through that, you'll start getting better at understanding that math. And if you understand math, your mathematical intuition of models will actually start getting better, trust me. Otherwise, you'll be the best person to learn all the APIs and all the functions, everything, and you'll be hyperparameter tuning. You don't know why you're choosing models. You'll start throwing things. Yeah, things will get serendipitous. You will be a human grid search, which is not efficient, right? Any questions? Good. Do you want me to cover more, or I think we have enough to go back and assimilate? All right. Thank you.